All right, so welcome to hydrodynamics for 2024. So today let's get started. So here's the syllabus. The syllabus should be on Canvas. I hope everybody has access to Canvas. Canvas mostly has all the things that I needed to have. So hours now. Clearly you found that. If you didn't, be there. So Tuesday, Thursday, 9:45 to 11, that's right now. Office hours I usually set kind of as necessary. Usually I set them the day before homework's due because I know that's when everybody's going to do the homework. And that'll fluctuate. Sometimes that's on Tuesday, sometimes that's on Thursday. If you need to talk to me about anything or whatever, just shoot me an email, and I'm usually pretty free. I prefer it if you set something up with me before, rather than just showing up, because I might be up to my eyeballs in code, and my ability to talk to people gets shut off when I'm programming. So it's very difficult to be a conversational person and coding at the same time. So you get a lot of blank stares. I'm never mean, I'm just kind of stupid looking. My email's the best way to get a hold of me is dccollins@fsu.edu. That being said, if you just show up in my office, I'll be happy to see you. But it helps my workflow if I know who's coming when. Oh, I gotta pass out an attendance sheet. The syllabus is like my to-do list for the first day of class. Where's my paper? Does anybody have a blank piece of paper? Oh, there it is. Oh, here it is, and I'm not found it. Here you go.
Just my name?
Your name and your FSU ID is probably good. So there's that first period or first day drop thing where they drop you if you're not there on the first day. I have, in my decade of being here, never successfully clicked on everybody's attendance, and nobody's ever been dropped. So I probably should care about it more than I do. But okay, so the book we're going to be using is Anurag Rai's Choudhury's Plasma Physics, an Introduction for Astrophysicists. There's not actually very much astrophysics in this class. I use it for an example for sometimes because it's a great laboratory for hydrodynamics processes. But there's really very little actual astrophysics in the class. So all of the astrophysics is, here is a spherical example. It's a star. We like spheres because we can do math on spheres. And stars are basically spheres. So we're going to cover the second quarter and the fourth quarter of the book. So the book is really nicely laid out. And if you have a minute, I would recommend reading the first 3 chapters. So in the first 3 chapters, he starts with gas is made of atoms. How do you describe fluid dynamics? So he builds up a whole theory of fluid dynamics through Boltzmann's H theorem and quantum mechanics and scattering. And all stuff that I don't think you guys have seen any of that stuff yet, so it's kind of not where we want to start. So he starts with this very kind of philosophical attack of building up hydrodynamics from the ground. And then he starts with, okay, we'll start with just a continuous fluid. So that's where we'll start, because that makes sense. So we're going to start with a continuous fluid. So I've got a fluid that exists at all points in space. He goes through and builds that up from having a collection of particles that are isotropic and statistically well behaved. But it's very cool, but we don't need it. So we could just start in chapter 4, and that's a great place to start. So we'll do 4, 5, 6, 7, and 8, and then we'll jump to, and then the second half of the book is plasma physics. So in chapter 10, he starts with plasma physics, and plasma physics is really beyond what we're going to actually get into in this class, just because you really need E&M. You really need to spend a whole semester on proper, pure two-fluid plasma physics. But that is basically describing a fluid where the electrons have started to come off the atoms. So so he builds that up from basically first principles, and then he gets to the MHD approximation, which is when you assume that things are large and slow for some value of large and some value of slow, and then you can ignore the electric field, and then you're left with something that looks like Navier-Stokes plus a magnetic field term. So the plasma physics we'll do is through the MHD approximation. I'll say all of that again in a second. So basically, we're going to cover about half the book. There's a reading due Thursday, so there will be readings. Many of you have had class with me, several of you haven't. But readings are a regular part of our coming and goings. Hey, welcome. You want to sign in and pick a seat? The chapter is, I know that not everybody's going to have the book by tomorrow, so the chapter is on Canvas. So readings are always due, so I might say that it's due Thursday, I mean midnight the night before, so that I can grade it before class and then we talk about it in class. So formally it's due tomorrow night at midnight. I'll talk about readings and what I expect from readings. It's not a big deal. It's kind of a long chapter and it's mathematically kind of a beat down, but I don't expect you to read it and understand it entirely. So I'll talk about that in a second. Okay, prerequisites. Really all I need is vector calculus and basic physics. So as long as you understand vector calculus and you have seen F equals ma and hydrostatic pressure and the basic physics stuff, we'll build from that. Formally, the prerequisites are Mech 1 and math physics, because if you have Mech 1 and math physics, then there's more things that we can do. So the more mathematical tools we can throw at hydrodynamics, the more fun things we get out of it. And I think everybody's more or less sorted with that. So, so formally, these are the prereqs, but the university does not have a mechanism for eliminating people for prereqs. So it doesn't, nobody's really checking. That being said, I do want everybody to be successful. But I think, I don't know, I think I'm pretty familiar with all of you guys. I think everybody's going to be great. So let's talk about what we're going to do. So we're going to talk about Navier-Stokes, which is the main equation that we'll be talking about, and Euler, which is Navier-Stokes minus a term. And we'll talk about simple things like how fluid goes down a river. And that's a relatively straightforward problem, which you probably did a little bit in 2048, or 2040, yeah, 2048. So we'll start off with basic hydrodynamics. And one of the things that I want you to be able to do, one of the things that sets this class apart from E&M or quantum, is I want you to be able to derive the constituent equations from first principles, which they don't show you how to derive Schrodinger's equation in quantum mechanics. Sometimes they do, but that's not how the theory developed. He kind of pulled it out of magic. He said, I bet this was right, and he was right. You can derive it from lots of ways, like you can take a wave equation with a relativistic mass term and linearize that, and you get Schrodinger's. So there's several ways you can get Schrodinger's equation, but it's not intuitive. And similarly, Maxwell's equations. Maxwell's equation was cobbled together by a bunch of weird things that people noticed, and then they had these weird relationships that Maxwell organized, and then later we realized that, oh, you can derive Maxwell's equation by taking relativistic action, minimizing a relativistic action in 4 space, and you can derive Maxwell's equations. That's a pain in the ass. I didn't do that until graduate school, so it's not. But hydrodynamics, we can start and say, here's continuity, mass is conserved. So what does that mean if I'm going to write down a math equation that says mass is conserved? What am I going to do? How am I going to write down an equation that says F equals ma for a continuous fluid with viscosity? So we'll talk about all those things. But one of the things that I like about this class is you can sit down and start with nothing other than a basic physics equation and generate the constituent equations. So we'll talk about waves. We'll talk about water waves, and we'll talk about sound waves. Bonus points if you can name that guy. Bonus points if you can name that wave. Nobody? Anyway. This is Jerry Garcia and their famous wall of sound. This is only a fraction of it. This is like a quarter of the wall. They had this enormous wall of sound that they would carry around in the 70s. And this wave is Chopu in Tahiti, which is where the Olympics were. We're going to talk about fluid instabilities. So fluid dynamics, laminar flow is beautiful but boring and doesn't get you very far. So we'll talk about instabilities. And there's a whole list of 2-name instabilities like Kelvin-Helmholtz and Rayleigh-Taylor and Rayleigh-Bernard and Rickmeyer-Meshkov that for some reason all get 2 guys' names associated with them. And then the Jeans instability, which is how stars form. So we'll talk about taking the Navier-Stokes and continuity equations and seeing where they are stable. So we'll do stability analysis of this. And then interesting physics phenomena comes out of it. I don't know if you can see these curly these curlies on this cloud. But this is a natural physics phenomena that develops because there's a shear flow. The flow is moving in opposite directions. And when you have that, things will roll up into these beautiful rolls. I lived in New Mexico for a couple of years, and the clouds would do this occasionally. But that's because I would start my trip home on one side of a 90-mile wide valley and end on the other. So there's this just vast sea of air in the middle. And so it was nice and laminar, so it would do things like this. So anyway, so we'll talk about fluid instabilities. You play. We'll talk about convection. So why does this do what it does? So you can see this looks like magically materializing cracks in the earth. So this is molten lava, and it's boiling up from the bottom. So it's hot on the bottom, and so it convects and rolls, and we'll talk about the size distribution of these rolls, because that's pretty fun. We'll talk about vorticity, which is basically fluid spinning around. So here we're going to see two things. We're going to see a vorticity dipole, which is basically like a smoke ring, except it's in water. If you've ever blown a smoke ring or seen somebody blow a smoke ring, that's a dipole in vorticity. It's essentially rolling outwards as it travels forwards, which is the reason that I started smoking in college, is to blow smoke rings with my then girlfriend, and now wife. You'll also see this delightful little dude who totally gets sucked up in that. Can you see that?
I think if it's show the slide, it'll be easy.
Yeah.
Contrast.
Let's do that. Let's do it again because it's really funny. So here's this little dude.
Whoa. Oh my God.
And he totally gets rolled up and spit out by that bubble.
Like a roller coaster.
I know, right?
He got off and was like, whoa.
I know. I bet he puked. So we'll talk about that, and that's one of the. Where'd my mouse go? We'll talk about turbulence a lot. Turbulence is really my bread and butter. It's what I do. Turbulence underpins all of my science research, and is the only thing that I do for a lot of it. Some of the papers that I write is just on turbulence. So turbulence has been described as the last great or the last open problem in classical physics. Because, I mean, F equals ma works really fucking well. But we don't have a complete solution space to Navier-Stokes equation, so we don't know. There's holes, like there's understanding that we don't have about Navier-Stokes that I'll talk about when I put it up, and then I'll show you more about it. But it's also incredibly important because it's how you mix the cream into your coffee. Without turbulence, it would take months for the cream to mix to your coffee if you just let molecular diffusion mix the cream in the coffee. But with the turbulent motion of just spinning your spoon around the cup one time, you make a lot of turbulence, and the turbulence mixes the stuff. So turbulence is important for a lot of reasons. It's physically interesting, and if you can solve it, you'll be famous forever. The other thing we cover is some plasma physics. So to within 0.1%, everything in the universe is either plasma or stuff we know nothing about. All of the protons in the universe are basically ionized. We get to live on a little patch of neutral ground, so that's kind of special. But the sun is a plasma. Most of outer space is a plasma. Big clusters of galaxies are huge masses of plasma. So basically everything is plasma. So plasma is fluid dynamics. Fluid dynamics only has short-range interactions, but a plasma adds a long-range interaction to the physical system. And we'll talk about that. So we're going to do this in the and fluid is when you take the magnetic and electric fields and turn them all the way to zero, you get a fluid. We're going to work in the MHD limit because that's what we can squeeze into one semester. Also, it's a very powerful approximation. So basically when we assume that, so you know Maxwell's equations couple the electric and magnetic field. If you assume that things are big for some value of big and slow for some value of slow, then you can average out the electric field, and you're just left with the magnetic field. Then I'll show you how that works later. And then you get magnetohydrodynamics. And this is a useful limit, but it describes lots of things. Most of outer space is well described by MHD. A lot of terrestrial phenomena are also described by MHD. And I'll talk about when MHD is appropriate and when it's not. So these are astrophysical plasmas. There's other plasmas as well. Here's a fun one. So this is a loop of magnetic field on the sun. Oh, you can't see that. Nope. So this is a loop of magnetic field on the sun. So this is the magnetic field runs through here, and then the gas is constrained to move along the magnetic field. And that's actually one of the first things that you're going to do. The first hard proof you're going to run into is why is fluid constrained to the magnetic field? We're actually not going to do that. We're going to do a corollary of it. But it winds up being the same physics. So stuff gets trapped in magnetic fields, like this magnetic field on the sun. And the magnetic field has energy that it can dump into the sun. Okay, so this is a list of the major topics. I think I still like all these things. I want you to be able to derive Navier-Stokes, perform several standard calculations, understand the major instabilities. I say in astrophysics, but I mean in general fluid dynamics. I started teaching this class as fluids for astrophysics, but then we realized that it's fun and everybody can do it. We don't need to limit it to astrophysics. So understanding when various things can be ignored is an important job that you have as a physicist, is understanding when you can ignore stuff. Because the whole shtick of being a professional physicist is writing down the system and throwing out all the crap that you don't need so that you get a linear equation so that you can solve it. Because we don't really know how to solve anything but linear equations at the end of the day. Everything else gets really hard. So we'll talk a lot about when you can throw out the viscosity term, when you need to keep it. We'll talk about turbulence, we'll talk about the Kolmogorov spectrum and Reynolds decomposition, which are fun and interesting. We'll get there. We'll talk about the hydromagnetic waves. So these are waves along the magnetic field in the plasma. We'll talk about instabilities with MHD. And then if we get there, so depending on how fast I talk, depends how deep into chapter 15 we get. So chapter 15 is how magnetic fields amplify themselves when you have something like the sun. So we'll get there, but we'll see how far we get. So let's see. Okay, so that's the basic motivation. So the details. So there's reading and class participation. That just means show up. Homeworks, final, and a midterm. Let's see. So readings. If you've taken a class with me before, the readings work the same. If you haven't, they're really pretty basic. So I'm going to assign a reading, and I want you to summarize it, whatever that means for you. So if it's just the section headings, and then I didn't understand Kelvin's circulation theorem, which I do expect everybody to say because it's confusing. Not to be intimidating, but the first time you go through it, you're like, boy, that was hard. And then you go through it again a couple of times, and then you understand it because it's a complex three-dimensional derivation. So it takes a second to get. Well, I'll get there. So tell me what you read about. Ask some questions about it, and tell me how long it took for you to read it. So I can gauge how everybody's doing. So how long did this take you shows up on everything that I assign. So every homework should have a how long did this take you question that's worth 2 points. That's useful for me to gauge where you guys are at with the material and whether or not the material was too hard or too long. These readings are kind of long. I do recognize that. So don't kill yourself. But do make an attempt. So the purpose of the reading, so do midnight the day before class. So it'll be like midnight tomorrow is the first one. I check everything when I get in at about 8. So as long as you've turned it in before I start looking, that counts as a win. That being said, you should practice good sleep hygiene and not stay up until 4 a.m. doing my homework. sleep hygiene is so important for your mental health. That's not something I learned until I was like 40. So, okay. So mostly I want the reading summary so that you guys are putting your brains on the things so that the first time I start to talk about turbulence, it's not totally new for you. You've at least seen the things that are going to be confusing, so then I can go over and make them not confusing anymore. And the grading rubric, 2 points if you did it, 1 point if you super half-assed it. So far, that's a really low bar. So turn something in. That's really all I'm looking for. And so I use this in 2 ways. First, I use it to prime my brain for what I'm supposed to talk about. And second, I'm priming my brain by way of what you guys are seeing and understanding. If everybody gets through the reading and everybody gets stuck on the same thing, then I'll spend a bunch of time on that. So the readings are really valuable for me to understand where you are. It's the way I can have a conversation with 20 people at the same time. Homework. So homework will be due again midnight the day before class, and you'll turn it in on Canvas. Cell phone pics are fine. Please make sure your cell phone pics are clear and legible and I can read them and they upload properly, so double check. Yeah.
Do you have a TA?
No.
Oh,
It's just me.
okay.
Yeah,
I'm just-
there's a TA deficit these days, so I didn't get one, but that's all right. I don't mind doing the grading, because again, that's part of the conversation that I can have with you, is seeing how you guys are doing this stuff. So for a class this big, I don't need a grader. For intro last fall, I had 30, and that was a little harder because I didn't have a grader, but. Okay, so lateness, I want to see it when I get in. If I have it before the end of the day, I'll take off 20%. If I get it after I post the solutions, I'll take off 50%, but that's good until the end of the semester. So if you mess up and miss an assignment, I'll accept it late until the last day of class. I don't want it after that. It's not worth it, because then we have the final. Like, I want you to do all the stuff in advance of the last day of class. So if something falls off your plate, no, don't freak out too much, but get it done as soon as possible. And sometimes the homeworks are going to be long, so try to stay on top of it. There'll be, I think, 6 homework assignments, so kind of every other week or so. I'll pull up the schedule in a second. So this is the order that we're going to do things in. We're going to start with chapter 4, which is ideal fluids, and we're only going to spend today and tomorrow, or today and Thursday, on chapter 4. It goes by kind of fast. The only things that we really want to get out of, well, there's several things that we want to get out of it, but the important things are Euler's equation and the Kelvin circulation theorem. Those are the 2 key things. Then there are also some hydrostatics and some other hydro things that we'll talk about a little bit, so that might spill into next Tuesday. Then we'll talk about viscosity, which is weird and takes everybody a minute. That's chapter 5. Then we'll talk about compressible fluids, and that's where we get to sound waves and shocks and fun things. Then we'll talk about linear perturbation, and I'm going to spend a bunch of time on perturbation. How many of you guys have seen perturbation theory somewhere? How many of you guys are happy about perturbation theory and feel like you kind of get it?
Are you?
Yeah.
Are you?
Comfortable with perturbation theory?
Happy about it?
Oh yeah, it's great fun.
Okay.
I love perturbation theory. So, but it took me a long time to get my head around it. So this is why I'm going to spend some time on it, because it's great. You take an equation that you don't know shit about, and then you turn it into a linear equation, and you solve it, and you're done. It's pretty nice. So it works out great. But there's some finesse to it, because the technique is really not super painful, but there's some stuff that you got to go through to make it work. And then if you get it to work, then it's very easy. No, not very easy. If you can get it to work, then it's successful, and you have an answer to that equation that you wrote down, which may or may not be right. I spent a lot of time the last couple of days on working in the everything is linear limit, and I hope that everything's right for research. Then we'll talk about turbulence, where linear perturbation fails completely. So we'll do it, and then I'll show you where it doesn't work. We'll talk about all kinds of fun stuff. And then we'll talk about MHD, and then we're starting to get into, we'll go through MHD and MHD stabilities and MHD waves. So we'll repeat some of the stuff that we did again, with magnetic fields, so we'll see what magnetic fields do. And then we'll talk about the topology of magnetic fields, how are they wrapped around each other and connected to each other. And then we'll talk about how magnetic fields build themselves in dynamo theory. And that's all pretty fun. And this stuff, the last 2 chapters are where things get experimental and the book gets out of date. Because the book was written in '95, and a lot of this stuff hasn't changed, but some of the later stuff, the dynamo stuff and the reconnection stuff has changed. Okay, so the schedule is here. Let's click on it and double check that it works. I made the mistake of putting the schedule in, I said open, right? There you go. Where the hell am I? Do the thing. Oh man. Making me look like a dumbass. Okay, so here's the schedule. And so mostly it goes through what I just said kind of in detail. The important bit are when the readings are and the homeworks. So this is an approximate due dates for readings and homeworks. Only the first reading actually exists in Canvas right now, but I'm going to make the rest of them later today. I'm pretty sure that I'm going to basically stick to the schedule. So unlike, so those of you who took Intro to Astro with me, one of the big differences between this class and Intro to Astro is I've done this one a bunch of times, so I'm not nearly as scattered. Not to say I'm not scattered, I'm still scattered as hell. And then the midterm, where did I put the midterm? So the midterm is nominally on the 22nd of October. Probably not going to be sooner than that. Hopefully not a lot later than that. But so nominally the 22nd of October we'll have the midterm. And let's see. This sums everything up. Here's the grade book. Reading and class participation are both 5%. Homework is 30%. The midterm's 25. The final's 35. And then that's the grade breakdown. Okay, does anybody have any questions on logistics and details? Everybody good? Okay, I am going to, where am I on time? Where's the clock? Oh, I still got 45 minutes, yay. Do I need anything else? No, now we're going to talk about math. So now we'll go over here, turn you off. We'll open this up. Turn this off so I'm not blind the whole time. All right. That's not the right thing. Is that the right thing? My notes. Okay. Chalk. I forgot his source chalk. Okay. Oh, that one failed immediately. I'm going to go over here. Let's see. Where am I? I'm off the camera there, so I am kind of constrained to these 2 boards. That's okay. Actually, I want to write it over here anyway. So, okay, so the Navier-Stokes equation, I'm just going to start with it. Says that dv dt plus v dot grad v equals -1 over rho grad p plus del squared v. This is Navier-Stokes, and this is the equation that we're going to spend basically the entire semester on. So we'll derive it, and I'll show you where all of these things come from. We'll linearize it. We'll see where the problems are. So, but I can point to where our knowledge is. So it's got 4 terms. dv dt, that's the partial derivative of v with respect to t. So that's just how things change in time. We have v dot grad v. So this is an acceleration, right? This is the other part of the acceleration. that doesn't make sense right now, but I'll show you in about 30 seconds why this is also part of the acceleration. But this is v dot grad v, and grad, what's grad? I'll talk about grad in 4 seconds. Who is that? Is that the projector showing up? Anyway, I just want to make sure there's not a bomb. So this term is fascinating and a pain in the ass, and some of the times we're going to try to get rid of it because this is where all the problems come from, but it's also where all the beauty comes from. So this is where all the complexity comes from. Grad P is just pressure gradients, so that's just force from the fluid itself. And then, oops, I missed an eta. Grad V, we'll run theta for now. Eta del squared V, and this is shear. So this is the time derivative. That's really what we're looking for. This is the nonlinear term, because it has 2 V's in it. That makes it not linear in V. So it's like the square in V. This is force, and this is shear. And we'll talk about what each one of these does in a second. But I want to put up the other equation that's going to be crucial for us. The other equation is continuity. Continuity says d rho dt, so the time derivative of rho plus div del dot rho v equals 0. Okay, I'm going to take a minute. I want to talk about, yeah, I got all those on. Okay. So I'm just going to leave that up because that's where we're going for the whole thing. Let's see. They don't want to listen to us. Okay, let's break everything down. Let's start with V. What is V? V is the velocity of the fluid. So we have a continuous fluid that fills all of space and is parameterized by position, x, y, z. So it's a vector field. So it has a Vx, let's call this just x vector, a Vy, let's call this x vector, and Vz, x vector. So this is a vector. So it has 3 components, and these 3 components are separate, but also not separate. So in the equation, sometimes they get to be separate, and sometimes they have to depend on each other. In ways that we'll see as time goes on. Rho of x, y, and z is the density. And this is in mass per volume. So it has to be in mass per volume because it's an intrinsic quantity. Yeah?
That would be the one without a vector on that following term?
Cool.
Okay.
I do appreciate I am going to make mistakes on the board because I am a space cadet. So please ask. Because sometimes it's innocuous like a vector sign, but sometimes I'll just write the wrong ass thing. So definitely holler if I say something wrong. So density is mass per volume, and so we want to talk about intrinsic quantities and not extrinsic quantities because the fluid in the room occupies this much space. And so if I wanted to talk about the mass of the room, I would take the density of air and multiply by the volume of space, and I would have a huge mass. But then the total volume of space doesn't matter to what the air is doing when I wheel my hands around. It doesn't care about that wall. It doesn't care about the total volume. It just cares about the local properties. So fluid dynamics is, until we introduce gravity or magnetic fields, is entirely local. And even then, they become basically local. So we need to deal with the intrinsic variables. So velocity is an intrinsic variable, and everything's going to be in a mass density. Really what that means is just if I have something like mass is conserved, density is going to be conserved because it's mass. Density is going to be conserved in this way we'll talk about that in a second. But the conserved quantities are going to be per unit mass. So we'll talk about momentum as well, and that'll be momentum density. I'm going to never remember to say momentum density. I'm just going to say momentum, and that's going to be in, what's the units on momentum? What's the units on momentum? I don't have to think about it. You guys do.
Kilogram meter second.
Right. So now we're going to be, so for momentum, that'll be P, little p. That's usually in kilograms meter per second squared, right?
Just the second.
Meter per second.
Meter per second.
Yeah.
Right. We're going to be dealing with momentum density, which is going to be this per meter cubed, so then we get a meter squared in the bottom. Also, this starts to look like a pressure. Pressure, what's pressure?
Newton per
What are the
meter
units?
squared.
What's that?
Newton per meter squared.
Yeah, a pressure is a Newton per meter squared, or
kg
kg
per
per
meter squared.
second per meter squared.
say it again.
Second per meter.
Yeah.
Right? Per meter squared, yeah. No, per meter.
Kilogram meter per second
Yeah,
meter
yeah.
squared per meter, right? This is already a density. I can think about this as an energy density as well. So it's a Newton per meter squared, so that's a force per area, or I can think about, so you remember the work is F times X, right? So a joule is a Newton meter. I can think about this as a joule per meter cubed. You see that? So pressure is energy per cubic per volume, or force per area, depending on how you need to view it. So both are acceptable ways of thinking about things. Also, it is very important that you learn the Greek alphabet. This is rho, which is for density, and this is P, which is for pressure, and that's momentum. Momentum gets a hat on it. I cannot distinguish capital P and lowercase p on the board, so momentum gets a vector. There, you make sure that you write your rows like a row. Okay, now vector stuff. So that's the basics. So that's how we're going to start. Now let's do calculus with these things. This is a vector field and a continuous vector field. So when we do calculus on it, we have to use all of the power of three-dimensional continuous calculus. So how many of you are comfortable or how many of you have seen Einstein vector notation?
What does that mean?
That's so what is this?
It's,
Dot.
yeah, dot product, which is the element.
Are we good with dot product? I'm going to have a homework assignment on some of this, so if you're a little rusty, that's okay. There'll be a space for you to make sure that we ask that you stub your toe on all of these low-hanging corners early. So this is a dot product. So when I can write a vector as v, or I can write it as vi. So this is a vector because it has a subscript that is hanging out by itself. If I have, say, vi, now I have a repeated index, and I'm going to sum over it. So this is a scalar. This is the dot product of v with itself. So at some points in time, this is the energy. Well, if mass is conserved, if mass is constant, then energy is 1/2 mv squared. And if m is just 1, it's just v squared. So this is just the energy sometimes. Sometimes it's not. Sometimes it's compressible and you need the rho. I'll explain all that later. So this is the dot product of v with itself. How many of you are comfortable taking the cross product using this notation?
Less.
Could somebody yell out what it is?
Oh.
If I've got A cross B, so there's a thing I got to use.
Epsilon ijk.
Epsilon ijk. And then what? A j b k. Okay, so epsilon ijk is the Levi-Civita or totally antisymmetric tensor. So, so epsilon I, j, k is 1 if I, j, k are cyclic, minus 1 if I, j, k are anticyclic, and 0 if any of the indices are repeated. So I, j, k are going to become 0, 1, and 2 for my x, y, and z components. So the options are 0, 1, 2, 1, 2, 0, 2, 0, 1, 0, 1, 2. So it goes in a circle. So you can have 1, 0, 0, 1, 2, 1, 2, 0, 2, 0, 1. Those options give you 1. Going backwards, 0, 2, 1 gives you minus 1. And those are the only ways that you can arrange them. Either they're in order or they're in backwards order with some permutation, if they're all different. If any one is repeated, it's the same. So if I'm going to take the dot product, if I'm going to take the cross product of two vectors, this is the free index. So how many free indices are on this thing? Is this a vector or a tensor? How many free indices are here? I've got this is a repeated index and this is a repeated index. And we sum over the repeated index so they go away. So we only have one free index, and it's the first index on the Levi-Civita tensor. That being said, I could write it as the other index, because I can permute these whatever I want. As long as it's cyclic, I can make this I and j, and that's perfectly legitimate, but it's a lot more confusing. It's best if you just try to leave the first index on the Levi-Civita as the free index, and then the other two are the ones that get summed over. Because it's cyclic, you can write it down a bunch of different ways. So if I was going to take the cross product of two vectors using this, I've got ax, ay, az, and bx, by, and bz. These are my two vectors. The cross product is going to be epsilon ijk, a, j, b, k. So epsilon 0, a1, b2. So I got a1, b2. That's the cyclic way to do it. So it gets a plus 1 minus a2, b1. That's the anticyclic way to do it. And those are your options for this sum. So what I'm doing is, so I've got two double sums. I've got a sum over, I've got a double sum. I've got a sum over j and a sum over k. We sum over both of those, and so you write down every possible combination with 0 being here and 2 and 3 in either of those, and there's only two choices that doesn't repeat an index. And that's these. So this is C0. And then we go through, and then C1 is going to be A2, B0 minus A0, B2. And then you do the same for the third one, whichever. If you get it now, cool. If not, I can do it again. Somebody. Okay, so we're going to use these guys a lot because things get very confusing when I write down this second term, which I'm going to write it down, and then I'm going to show you where it comes from. Actually, I got a couple things first. Yeah. So let's talk about nabla. What's this guy? Grad, what's in it? What is it?
It's the partial derivatives of all the dimensions.
Right. And it is a vector. So this is a vector, and it is d by dx, d by dy, d by dz. I'm really lazy, and so I usually skip a whole d. So this is the derivative with respect to z. Does anybody hate that really a lot? Is everybody all right with that? So we have the derivative with respect to x. Actually, since we're just starting, let's not get too sloppy too fast. This is d by dx, d by dy, d by dz. And it's a vector of verbs that does stuff. So nabla is a verb. It does things to other things. But it's also a vector, and you can do things with it. So you can take the dot product and the cross product with this guy. I can dot things into it, and I can dot it into things. So two things we like to do are div v. So this is nabla dot v. So that's going to be v is vx, vy, vz. So nabla dot v is going to be d by dx of vx plus dy by vy, dvy, dy plus dvz, dz. And I'm going to write this down in Einstein notation as divi. I can also write divj. So do you know another word for this thing? This is the divergence of the velocity. The divergence of a vector field is nabla dot that vector field. And that's basically how much is coming into or going out of a certain area, which is important as we talk about continuity. This, how many free indices are on this? 2. So that makes it a what? That makes it a tensor. So now this is a 2-index object, and I've got an I and a j index, and this is a tensor, which is like a matrix. So just think about this like a matrix. So this is going to be a matrix of derivatives. This is the shear matrix. This is going to be dx vx, dx vy, dx vz, dy vx, dy vy, dy vz, dz, that's an x, dx vz, sorry, that should be a y, it's an x and a y, x, 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 y, x, y, z, x, y, z, dy, v, z. Sorry, shit. Remember how I said I'm kind of a space cadet?
Wait, is it shear S-H-E-E-R or S-A? Okay.
Shear is moving, two things moving back past each other. So dx vx, dx vy, dx vz, dy vx, dy vy, dy vz, dz vx, dz vy, dz vz. So this is a tensor that has 2 indices on it. These are going to show up all the time, and the only thing you need to worry about is how many free indices you have. That's the important thing. And which index are you dotting into when you do dot things into things. We're not going to get too deep down this rabbit hole. When you get to ENM and GR, this gets really hairy. But we will use this a lot because because of the convective derivative. So let's talk. The other thing that you can do with a vector is curl of v, and that's nabla cross the vector. And there you do the same thing, except instead one of the vectors being a vector, one of the vectors is now this verb. It's this vector of derivatives. So you'll get something like dy vz minus dz vy. And then 2 more terms that look like that. I'll make you do that for a homework. Okay. This is all hopefully a review, but I want to say all this, like I know this might be kind of reviewy, but I want to make sure that I say all that because then when I write down this thing is confusing. This second term here, v dot grad v. How do I write this down in summation notation? So here's a vector, and here's a vector. So what this blob says, and I'll show you where this comes from right now. I just want to make the connection with the vector notation. This is v dotted into this grad. So this is going to be vi d by dx I. So the velocity is dotting into the gradient. And then you act that on the vector. So in tensor notation, these guys will both get an I, and because it's a dot product, they're going to be the same I, and we're summing over them. And then this guy is another vector by itself. So this is a vector equation where I've taken the scalar product here, and I have the other vector here. That's horrible. Let me explain why it is that way. So this will become, you'll get comfortable with that. Let's talk about chain rule for a second. So if I have f of g of t, what is df, the full derivative with respect to time?
F prime of g of t times g prime of t.
Yeah. I hate primes because I get confused really
Okay,
fast.
so what do you want?
So this is going to be df
Yeah,
dg
right.
dg dt, right? So I want to say what is dv dt. Is that clock still running?
Oh, that clock. They don't have technology here.
I never started class. I'm stuck at the beginning of class forever. Shit. Yeah, it goes till 11. We got so much more time. I've been looking up there thinking I had 15 minutes left for like the last 5 minutes. No, I got 20 minutes left. Because I go to 11, right? Yeah, I still got 20 minutes left. Okay, cool. I'm not in a hurry. Okay, dv dt. Let us chain rule this, yeah.
Is there any reason to use partials there instead of like full derivatives for the chain rule?
Yes.
Yeah.
Yes. So, and that's an important question. When is it a partial derivative and when is it a full derivative? This is a full derivative because I'm saying that's what I want. And then when I go to chain rule it out, then I'm looking at, so this is all of the change of f when I change t at all. But I'm going to break that down into the change, just the change in f with respect to g holding everything else fixed. And then just the g with respect to t holding everything else fixed. Does that make sense? So in these two, we're fixing all of the other variables. But in this one, the variable is this and all of the change that comes with it. So now I can say partial f, partial t, and I can't decompose that any further because that's just like the explicit time dependence. So if f were equal to vt, then partial f, partial t would just be v, even though v has some time derivative as well. Does that make sense?
Yeah.
This will hopefully become more clear, but come back and ask me that question again. Also, come back and clarify when it's a full derivative or not, because sometimes my handwriting is hard to tell. I try to make my partials real loopy, and my full derivative is real straight. So let's talk about what the full derivative of velocity is with respect to time. So velocity, remember, is a function of position. And it's only a function of position. It doesn't have any explicit time dependence in it. It's just a function of position. So the full derivative with respect to time is going to be the partial derivative of v, and this is a vector, the partial derivative of v, so this is all of my terms, with respect to x, times the partial derivative of x with respect to t. Now, let's hold up there for a minute. Let's say for now that velocity is a function of x, which is a function of time. So we're just in a one-dimensional universe. What is dx dt? V, right? So this is just v times dv dx. That makes sense? So this feels a little dumb because chain rule you've just been seeing for years, right? So I'm just doing chain rule again, but this has incredible power because I take the time derivative of the velocity and I get it back out. I get the velocity itself back out. Plus the partial with respect to v with respect to t. So it may depend on it may have some by itself t dependence, but it depends on x explicitly. I think I said something that was confusing about 13 seconds ago, so if you can ignore that. So the full derivative of velocity with respect to time is going to be the partial derivative of velocity with respect to time, and that's just you hold everything fixed, so I just stay put in one spot, and I look at one little volume, my position is fixed, and I look at what the velocity is doing in this one little tiny volume of space. That's this. But this is what the velocity is doing, because as the velocity comes into this space, it's getting pushed around by other velocities and getting moved and changed by the velocity itself. So the velocity field affects itself as soon as you take a time derivative. And this is fascinating and a hassle and causes lots of interesting problems. This is where turbulence comes from, and this is where the complexity comes from. So if I do this for all three terms, then dv dt equals partial v, partial x, partial t, plus partial v, and the v's are vectors here, partial v, partial y, partial t, plus partial v, partial z, partial z, partial t. And this is just equal to v dot grad v. Let me write that up here so that it's higher. So I've got the full derivative of velocity with respect to time is the partial with respect to time. So that's just what happens if you're just sitting there. Plus I got dx, dt, dv, dx. And we're going to make this an I. We're going to make this an I. So now xi is x, y, and z. And here I'm summing over them because I got three of them. I got an x, I got a y, and I got a z. Yeah.
So okay, dv dx, that's the partial derivative with respect to x of every component in the v vector.
Yes.
Okay.
Yeah, I was a little sloppy in leaving this a vector. I could have been a little nicer and not let it been a vector. But this is for every component of the vector. So if I'm going to write this out, now I'm mixing notations, which is kind of obnoxious, but I'm doing it that way because it makes it more clear. Because I'm acting on this vector, so what I've really written down is three equations for each component of v. So v is vx, vy, vz, so I'll have one of these for vx, one of these for vy, one of these for vz. This bit is the same for all three equations. So the v dot grad is the same for all three equations. So this is dx dt, so that's v, and then I'm just going to look at this part. So this part is v, I, and this is d by dx, I, times v. Oops, that's not a vector anymore, because that's the component. Does that make sense? So this will get more confusing once you put your hands on it, and then it will become less confusing. Yeah?
On the other board, is that v dot dv dx?
Here?
No, there.
Yes.
Okay.
Because this should be a dot product because I've got three components. But if we just think about this, I can do this again by just talking about the vx component. So if I just say dvx, not a vector anymore, dvx dt is equal to partial vx, partial t, plus v dot grad vx. Yeah.
Yeah, so in that same equation with the v dot dv dx, I get that dv dx times dx dt is v dot dv dx. I get
Yeah.
that, but where does the dv dt come from?
This one?
Yeah.
That's just part of this. So I would also get partial f, partial t. It's just one of the things that comes out of the chain rule.
Okay.
So so when you do chain rule, it's all the partials with all of the dependents, and then the one by itself. So because it could have just some dependence by itself. Does that make sense? Okay. So what is f equals ma? Don't want to do that. Past me did it a certain way.
Are you looking at notes right now?
Was that?
Are you looking at notes
Yeah,
right
yeah.
now?
They're not very in-depth.
Oh, okay. So that's not for us. We don't see that later?
No.
Okay.
This is chicken scratch so that I remember what to vamp on. If I write out everything, then it becomes illegible very quickly. But if I do go through anything and you want to see me tech out any of these longer derivations, I can write up or put tech to a lot of the longer derivations that aren't in the book. But most everything is in the book. I try to stick pretty closely to the book because I think that's kind to the students. Yeah.
So like the second time that you where you're writing ddt, like the bottom line, the bottom version, there should be a fourth term over there as well. Oh, okay.
Yeah, thank you.
And that won't be a vector v, that would be a regular v.
This would be a vector v. So this is the vector, because it's the same vector that you're taking the derivative of. And not one of the components. The components only show up when you're breaking down the chain rule for the vector. Okay, so what we're going to do first is derive this part. This part, without the viscosity term, is called Euler's equation. And we're going to derive it yeah, let's do that now. So f equals what? ma. So now we're in a continuous fluid. So we don't want to deal with mass anymore. We want to divide everything by the volume. So we only deal with density instead of mass. So we have F equals rho dV dt. Let's talk about F first. So F comes from pressure. And if I have a fluid that has a certain pressure, you know what the air pressure is at sea level?
1 atmosphere?
What's that?
1 atmosphere.
1. That's my favorite answer to everything, because the answer is always 1 in the right unit. So it's 1, right? 1 atmosphere, which is actually a lot of pressure, 14 pounds of pressure per square inch, which is a lot when you think about 14 pounds and how big an inch actually is. But you don't feel that, because it's pushing on all parts of you at the same time. So you don't feel the pressure of the air. You only feel pressure when? When do you feel the pressure? So if I have a wall, and I have a pressure on this side and a pressure on this side, and these pressures are equal to each other, what's the net force on the wall? 0. But if this force is bigger than this force, then what's the net force going to be on the wall? It's going to be this way, right? So then you'll have a net pressure force. So there are much longer derivations than this, which is worth, I think the book goes through a better derivation than this. This is kind of half-assed. So which way is the direction? So dp dx, as I've drawn it here, goes this way. P is getting bigger that way. You know the force is in this direction. So the force on a fluid from its pressure is minus grad P. Why grad? Because this is just one dimension. I have 3 dimensions, right? And force is a vector, so force needs to be a vector, so I need to have the vector derivative. Right? So the force per unit volume is grad P. We're going to rewrite this as the force per unit mass. And that just gives us a 1 over rho here. Because really we're going to do everything with force per unit mass, and then we're going to go deal with the momentum per unit mass. What's the momentum per unit mass?
Velocity.
Velocity. So the momentum per unit mass is just velocity. So we're going to put this rho over here, because this is bad enough by itself. So I'm going to expand out. So on one side, I have minus 1 over rho grad P. And this term is relatively painless in most of your encounters with it, because you're just taking the gradient of a scalar field, so it's not something complicated to sort out. But on the other hand, we have the full derivative of v with respect to t, and as we said before, that's going to be the partial of v with respect to t. There's the vectors on the nobler there, plus all 3 of the subterms. So I got dv, dx, dx, dt, plus dv, dy, dy, dt, plus dv, dz, dz, dt. Simplify all that. This is just equal to partial v, partial t, plus v dot grad v. So now equals, we'll just write that over here, minus 1 over rho grad P. To write this in index notation, which is a lot more clear because you know what's being derivative by what and what dot product goes with what. So this dot product, this term is tricky because this dot product connects these 2 guys and not this guy. So I'm going to write this in tensor notation. It would be dvi dt plus vj dj vi equals minus 1 over rho di p. So I've just written down F equals ma, but it got really gross because we have this continuous fluid and it's a vector field. So now I've written it in component form. So I've got an I here. The j's, I've got 2 j's, so that's a contraction, so that it's a scalar now. Then I've got my I here. This one has to also have an I because all the vector components have to agree on both sides of the equation. Does this make sense? Everybody all right so far? More or less? There will be homeworks that wrap that up. So that is the first part of the Navier-Stokes equation. So we've got dv dt, v dot grad v, and then 1 over grad p. We'll talk about the del squared term next week. But I'm going to put it up because it's crucial, because the del squared term is how airplanes fly. Without that, you couldn't move around in the fluid. So it's very important. Okay, I got 5 minutes left. I'm going to talk about one last thing because I'm going to need it, but I'm only going to spend 5 minutes on it, so I might come back to it. Who remembers the fundamental theorem of calculus? Somebody? Somebody yell it out?
The integral of the derivative is equal to the function.
Yeah. Integral. I learned this. Calc 3, vector calculus, for me was an awful class. I got a C. I hadn't taken a math class in several years before I started taking calculus because I was a music major for a while. So I got to Calc 3 and I did terrible. I got a C, but I learned an enormous amount from this guy. He was an awful teacher, but I still learned a lot from him. It was a fascinating thing. The one thing that really the integral of d foo is foo. So, like you said, the integral of full derivative is the function. If this were partial foo, this wouldn't be true. This has to be full d foo. So what does that mean? That means that if I integrate some function, if I integrate the derivative of a function between a and b, I'm left with a function evaluated at the endpoints, a and b. So if I do that in one dimension, it looks like this. If I do that in 3 dimensions, it looks like this. The integral of div v, now there's another vector derivative that I can use, the cross product. We'll talk about that in a second. The integral of div v is equal to what?
The integral of v dot dA, or
V.
v squared of x.
Yes. Over the area. So you see it's the same thing. The derivative goes away, and we're left with just an evaluation on the surface. So I have some volume, and I've got some crap inside. If I want to evaluate the derivative on the inside, I'm going to integrate that. That just gives me the volume on the surface. And all of that is just the fundamental theorem of calculus. The integral of d foo is foo, just done in 3 dimensions. And you're left with another integral, but you've got fewer integrals by 1 because you've undid that derivative. The other weird way this shows up is Stokes' law, and this is del cross v around, who remembers what that, around the surface is equal to v dot dl around the perimeter. And it's the same thing. Now I got to do like this, and I got a vector field passing through it. I evaluate the curl of that vector field on the inside, and I'm left with just the value of the function, but you got to integrate around the loop around the side. Both of these are going to be useful for the circulation theorem. So Calvin's circulation theorem is basically just an application of Stokes' law applied to Euler's equation. And that is it for me for time. So you'll see this in the reading. Please do the reading. Put your eyes on Calvin's circulation theorem. If you get to the end and you're like, boy, I have no idea what that is, don't worry. We'll go through it and we'll take it apart and understand it. Because it is a little hairy, but it's not the end of the world. Okay, does anybody have any questions about logistics or anything? Or anything I said? Good. Sweet. Talk to you guys soon.